Carboxylic acids, as the name implies, are considered acids or an acidic functional group. This is due to the fact that the conjugate base of a carboxylic acid will be resonance stabilized. So here's an example with acetic acid, which has a pKa of about 5. When treated with base, it produces a conjugate base that has a negative charge. That negative charge will be resonance stabilized between two oxygens. Compare that to an alcohol like ethanol, which has a pKa of roughly about 16. When treated with base, it produces a conjugate base, which is not resonance stabilized. So that explains why carboxylic acids are more acidic than most functional groups, including alcohols. Carboxylic acids, like other acidic functional groups, are affected by electron withdrawing groups and electron donating groups. For example, here we have acetic acid, which has a pKa just slightly under 5. If we add an electron donating group, like a methyl group, notice the pKa increases, which means the molecule is less acidic. With halogens, which are electron withdrawing groups, the pKa generally decreases, and it decreases based on electronegativity. So the more electronegative groups would make the carboxylic acid more acidic. This is a result of these halogens withdrawing an electron density from the proton. So in the case of a fluorine, because it's a highly electronegative atom, it would place a high partial positive charge on the hydrogen of the carboxylic acid, which would make it want to react more like an acid. Another way of looking at it is if we take a look at the conjugate base of one of these carboxylic acids. So after we remove the proton, we're going to have a negative charge on the oxygen. And having an electron withdrawing group, for example here a fluorine, would mean that that negative charge would be stabilized more so than without the electron withdrawing group. The same thing or the opposite situation would occur if we have an electron donating group, which would destabilize this negative charge and make the conjugate base less stable, less likely to form, and therefore the acid would be less acidic in that case. Generally, the further away the electron withdrawing group or electron donating group is from the carboxylic acid, the less of an effect it has on the acidity. As an example, chlorine, which is an electron withdrawing group, if it's right next to the carboxylic acid, it lowers the pKa quite a bit. So it lowers it from 4.82 to 2.86 in this example. As we move that chlorine further and further away, notice the pKa starts to increase and essentially goes back to pretty close to 4.82. This is a result of the chlorine having less of an effect the further it is away from the acidic functional group. If we compare the acidity of a typical carboxylic acid on an alkyl group versus an aryl group, generally the aromatic ring will make the carboxylic acid more acidic than, let's say, a methyl group. One way of thinking about this is the hybridization of the carbon right next to the carboxylic acid. So in the case of benzoic acid, the pK is about 419, and we have a carbon that is sp2 hybridized. In the case of acetic acid, the pK is about 476, and the carbon next to the carboxylic acid is sp3 hybridized. We consider sp2 hybridized atoms if everything else is the same, more electronegative than sp3 hybridized atoms. So carbon, when it's sp2, is more electronegative than when it's sp3. One way of thinking about this is an s orbital is closer, or the electrons in an s orbital are closer to the nucleus because of the spherical shape, compared to the electrons in a p orbital, which are a dumbbell shape. So if a carbon has more s character, meaning a higher percentage of an s orbital, generally those electrons will be closer to the nucleus, and therefore we consider that atom more electronegative. When we add substituents around a benzoic acid, similar to substituents on an alkyl carboxylic acid, we can affect acidity. So electron withdrawing groups like halogens would generally make a carboxylic acid more acidic. When we add electron donating groups like alkyl groups, those groups will make the carboxylic acid less acidic due to electron donation. Here's an example with fluorine when it's ortho, meaning at the carbon right next to the carboxylic acid. So that would be this one here or this one here. The pKa is lower, so 3.3 compared to 419 without that substituent. When we move it to the meta position, it's slightly higher, so it starts to go back to 419 as we move further and further away from the carboxylic acid. And then the para position, if we put a fluorine at the para position here, the pKa is 4.1, so fairly close to benzoic acid. This effect that we're seeing here is called an inductive effect. So an inductive effect or induction is basically withdrawing electron density or donating electron density due to electronegativity differences. And this is typically done through bonds as well as through space. Some groups, like a nitro group, are electron withdrawing or electron donating, not only through induction, but also through resonance. As an example, when we have the nitro group at the ortho position, the pK is about 2.2. When it's at the meta position, it's 3.5. So this so far matches pretty well to what we saw with inductive withdrawing groups like the halogens, like fluorine. But notice in this case, when we place the nitro group at the para position, the pK is actually slightly lower than when it is at the meta position. So it's actually more acidic when it's at the para position. The way we can explain this is due to resonance. So if we look at the resonance structure below, we can explain this example. So with the para-substituted benzoic acid, we can move electron density away from the carboxylic acid and have a structure that has a positive charge right next to the carboxylic acid. That positive charge behaves like an electron withdrawing group, and it makes this hydrogen on the carboxylic acid more acidic. When we place the nitro group right next door to the carboxylic acid, the nitro group will, in one resonance structure, have a positive charge right next to the carboxylic acid. This positive charge, similar to what we saw with the para-substituted nitro-benzoic acid compound, will have an electron withdrawing effect on the carboxylic acid. It will make this hydrogen more acidic as a result. When we have a meta-substituted nitrobenzoic acid, if we try to draw other resonance structures, for example, this one here, we will have the positive charge always further away from the carboxylic acid than we did when we have an ortho or a para-substituted nitrobenzoic acid. If we try to draw other resonance structures, the closest we can get this positive charge would be either at this carbon or this carbon. And so it will never get as close to the carboxylic acids as we saw with the ortho substituted nitro compound. And so this explains why having a meta substituted nitrobenzoic acid, we don't have we don't have a compound that is as acidic as the para substituted example. Look at a few more examples of substituted benzoic acids. So the pKa of benzoic acid, as we mentioned previously, is 4.19. If we add a methyl group at the para position, it goes up to 4.38. So we can explain this by the fact that the methyl group and other alkyl groups are electron donating through induction. We have now three other examples or substituents in this slide here. So we have a methoxy group, which it leads to a pKa of 4.46 when it is at the para position of benzoic acid. A phenol or hydroxy group, it leads to an increase of the pKa value, and the amino group also does the same thing. So notice that the methoxy, the hydroxy, and the amino group are all making benzoic acid less acidic, not only then when it doesn't have any substituents, but also even when it has a methyl, which is an electron donating group. So how do we explain this? So we believe that these groups are electron withdrawing through induction. As you would expect, a highly electronegative atom like oxygen or nitrogen would make the carboxylic acid slightly less acidic, more acidic because of electron withdrawing through induction. However, how do we explain these values here? So it turns out that resonance has a bigger role. It is making benzoic acid less acidic through resonance. So what's common about these three substituents is that they all possess lone pairs on these atoms, so whether it's oxygen or nitrogen, and that lone pair is right next to the ring. So using this hydroxy substituted benzoic acid as an example, we can use the lone pairs on this oxygen to push electrons towards the carboxylic acid, and we could come up with a resonance structure that has this negative charge right next to the carboxylic acid. That negative charge behaves as an electron donating group, and it makes this hydrogen of the carboxylic acid less acidic. When the hydroxy group is ortho to a carboxylic acid, we can draw another resonance structure as shown here, where we push electron density towards this carbon right next to the carboxylic acid. That places a negative charge there, and that negative charge acts as an electron donating group, which will destabilize the conjugate base of this carboxylic acid, making it less acidic than if we did not have that ortho hydroxy group. When the hydroxy group is meta to the carboxylic acid, if we try to draw another resonance structure as shown here, so using this lone pair pushing electrons towards this carbon, we can place a negative charge there. That negative charge also acts as an electron donating group, but because it's not as close to the carboxylic acid as this negative charge when the hydroxy group is ortho or when it's para, as we saw on a previous slide, the negative charge here is not going to have as strong of an effect as an electron donating group. And so this compound here would be slightly or actually a little bit more acidic than the ortho substituted hydroxy compound and the para substituted hydroxy compound. This table here summarizes nicely how different substituents affect the acidity of benzoic acid. The first three examples, the nitro group, the nitrile or the cyano group, and an aldehyde generally will make a carboxylic acid more acidic, not only through induction, but also through resonance. And this is especially true when the groups are ortho and para. The next two, the bromine and the chlorine, are electron withdrawing groups, mostly through induction. And so the pattern follows that as the group gets closer to the carboxylic acid, the more of an effect it has. And so the further it is, the less of an effect it has. Methyl group here, as we talked about before, is an electron donating group through induction. And then the last three groups here, the methoxy, the hydroxyl group, and the amino group, are all electron donating, not mostly through resonance, but they are slightly electron withdrawing through induction. But overall, for the most part, they behave as electron donating groups because of the strong effect of resonance. And again, this is especially true when they're ortho and para. Nitriles are generally more acidic than alkanes, and this is due to the fact that the nitrile group can resonance stabilize a negative charge next to the nitrile group. Here's a couple examples, starting off with a nitrile. Typical pKa for nitrile, like acetonitrile, which is shown here, is around 25. A typical alkane is anywhere between 50 to 60 pKa units. If a base deprotonates a nitrile, we have this carbanion that is shown here. The same thing would happen with an alkane. However, in the case of a nitrile, we can resonance stabilize that negative charge, as shown, where the electron density can move into or towards the nitrogen to create this stabilized conjugate base. Since the conjugate base is stabilized, that means the acid is going to be more acidic, as the pKa show. In this question, we will rank the following three compounds in order of increase in acidity, starting from the compound that is least acidic. In a question like this, where we have to rank compounds in order of increase in acidity, we want to find what the differences are between the three compounds. In this case, we basically have three benzoic acid compounds with three different substituents at the para position. Benzoic acid has a hydrogen, then we have a 4-methyl substituent in one of the compounds, and then a 4-chloral substituent in the last compound. Methyl groups are generally electron donating, and they will make benzoic acid less acidic. A chlorine is generally electron withdrawing, and it will make benzoic acid more acidic. Therefore, the 4-methyl substituted benzoic acid would be the least acidic, followed by benzoic acid, and then lastly, the most acidic compound is the 4-chloral substituted benzoic acid.